It hangs above rooftops and tree lines with a familiarity that borders on intimacy, a pale surface bright enough to cast shadows on quiet streets. It seems almost within reach, close enough to measure against the width of a fingertip held at arm's length. Yet the comfort of sight conceals a separation that is vast and absolute. The moon drifts at an average distance of 384,400 kilometers, a span equal to roughly 30 Earth diameters, placed side by side in silent procession. Between the two worlds lies no gentle gradient, no gradual thinning of air that eases the transition, only a widening gulf of vacuum that begins the moment the atmosphere yields to blackness. Light itself requires about 1.3 seconds to cross that gulf. A beam reflected from the lunar surface leaves in stillness and arrives with a delay that the human senses cannot detect. Yet instruments record faithfully. Radio waves follow the same constraint, carrying voices and telemetry across space with a perceptible pause. Conversations cannot overlap naturally. Every exchange must accommodate the finite speed at which information travels. In that brief interval between transmission and reply, distance becomes tangible. It is not the dramatic stretch of interplanetary voyages, yet it is far beyond the comfortable immediacy of orbiting laboratories circling a few hundred kilometers overhead. Low Earth orbit remains cradled within the planet's magnetic field, sheltered from the harsher streams of charged particles that wander through deep space. The International Space Station moves at roughly 400 kilometers above the surface, a height that still belongs in many respects to Earth. Spacecraft there can return within hours, guided by established procedures and multiple landing options. The moon resides far outside that protective envelope. A vehicle departing for lunar distance leaves behind the safety of rapid rescue and the assurance of quick descent. Midway across, there are no emergency runways, no alternate ports, only trajectories governed by gravity and momentum. The sense of closeness arises from geometry. The moon appears large because it is physically large, and because it is our nearest celestial neighbor. Its phases change nightly, creating the impression of an active companion rather than a remote destination. Tides respond to its pull. Eclipses trace predictable patterns across calendars. These rhythms weave the moon into daily experience, softening awareness of the emptiness that surrounds it. The sky offers no scale markers to reveal how far away it truly is. Without reference, distance compresses into familiarity. Travel across this expanse demands precision sustained over days. After the engines fall silent and the translunar injection burn is complete, a spacecraft coasts through a region where minor deviations accumulate quietly. Course corrections must be calculated and executed with care, since small angular errors expand over hundreds of thousands of kilometers. The crew, if present, inhabit a volume no larger than a modest room, enclosed within layers of shielding that separate life from vacuum. Outside, there is no atmosphere to scatter sunlight, only stark illumination and shadow. Seen from Earth, the moon's brightness disguises its remoteness. Seen from the path between worlds, Earth diminishes into a luminous sphere suspended against darkness, and the idea of nearness dissolves into measured distances and signal delays. The illusion fades, replaced by an understanding, shaped not by sight but by physics, where every kilometer must be crossed deliberately, and every second of communication carries the quiet reminder of space stretched wide. There is a boundary that cannot be seen from any window, a gradual thinning, not of air, but of protection, where Earth's invisible shield begins to loosen its hold. Within low Earth orbit, spacecraft move through a region still wrapped in the planet's magnetic field, a vast structure shaped by molten currents deep within the core. Charged particles from the sun are guided along its lines, diverted and softened, their energy dispersed before reaching the altitudes where crews circle the globe. The station that drifts a few hundred kilometers above the surface remains, in subtle ways, inside Earth's embrace. Its path never strays far from the layered defenses that have guarded life for billions of years. Beyond that region, the geometry of safety changes. The magnetic field stretches outward in a long tail and compressed front, sculpted by solar wind, yet its strength diminishes with distance. A spacecraft departing for the moon crosses through zones known as the Van Allen radiation belts, where energetic particles are trapped and concentrated. These belts can be traversed quickly along carefully chosen trajectories, but they mark a transition from relative shelter to exposure. Past them lies interplanetary space, a realm where galactic cosmic rays move at near light speed and solar particle events can surge outward without warning. The flux of radiation increases not as a sudden wall, but as a persistent background, a steady rain of high energy particles capable of penetrating materials and altering living tissue at the cellular level. During the Apollo missions, crews passed through this environment for brief intervals. Their journeys were measured in days, and mission planners relied on timing and probability to reduce exposure. Since the last departure from lunar distance in 1972, no human presence has extended continuously beyond low Earth orbit. Decades of habitation have taken place close to home, refining life support systems and orbital operations under the relative moderation of Earth's field. The experience of deep space, by contrast, remains limited to those earlier voyages and to uncrewed probes that feel no biological consequence. Radiation in deep space is not merely a statistic recorded by dosimeters. It influences design at every level. Spacecraft require additional shielding, yet shielding adds mass, and mass demands greater propulsion. Materials must be selected for their capacity to absorb or deflect energetic particles without producing secondary cascades that complicate exposure. Electronic systems must endure ionizing events that can flip bits in memory or disrupt processors. Redundancy becomes essential, not as an abstract principle, but as a quiet safeguard against invisible disturbances that accumulate over time. Autonomy emerges from distance as well as hazard. In low Earth orbit, communication delays are negligible, and ground control can intervene swiftly when anomalies appear. Farther out, the growing separation imposes delay and limits the possibility of real-time guidance. Spacecraft traveling beyond the magnetosphere must navigate, diagnose, and respond with increasing independence. Crews must rely on onboard systems and their own judgment, supported by procedures designed for contingencies that may unfold beyond immediate assistance. The architecture of mission control shifts from active steering to strategic oversight. As a vehicle moves outward, Earth recedes not only in apparent size, but in practical reach. The familiar network of tracking stations, recovery forces, and rapid return options fades into abstraction. What remains is a craft sustained by its own integrity, carrying within its hull the fragile continuity of human presence. Outside, particles trace silent paths through vacuum, indifferent to intention. Beyond low Earth orbit, exploration becomes less a continuation of orbital routine and more a step into a region where protection thins, autonomy deepens, and the margin for error narrows into the quiet arithmetic of physics. Before any spacecraft can drift outward into silence, it must first climb through weight. Not the simple weight of metal and machinery resting on a launch pad, but the deeper weight imposed by a planet that has gathered oceans, mountains, and air around itself for billions of years. Earth's gravity well is not a metaphor, but a measurable depth, a curvature in space-time that holds everything close. To rise from the surface is to move against that curvature, to trade chemical energy for altitude and speed until falling sideways becomes possible and falling away becomes achievable. Escape velocity, 11.2 kilometers per second, is often quoted as a single threshold, yet it represents an accumulation of motion that must be earned. No vehicle leaps instantly to that speed. Instead, engines ignite and continue burning, pushing propellant downward in controlled torrents while the vehicle strains upward. In the first moments, atmospheric drag presses against its skin, compressing air into shock and heat. The rocket must accelerate, not only upward, but fast enough to outrun gravity's steady pull, which subtracts from its velocity every second the engines fire. Fuel is spent simply holding the vehicle against the planet's insistence on return. The lower atmosphere thickens resistance. As speed increases, drag rises sharply, demanding careful shaping of ascent profiles. Guidance systems throttle engines and tilt trajectories to balance structural stress with efficiency. Gradually, the air thins, and the burden of drag lessens. But gravity does not fade with altitude as quickly as intuition suggests. Even hundreds of kilometers above the surface, Earth still commands with significant strength. To enter orbit requires not climbing straight up, but accelerating sideways until forward motion is so great that the planet curves away beneath the spacecraft. Only then does continuous freefall become stable motion rather than descent. This demand for velocity explains the disproportionate scale of launch vehicles. Most of a rocket's mass at liftoff is propellant, cryogenic liquids, or refined kerosene stored in vast tanks. The payload, whether crew capsule or cargo, occupies a comparatively small fraction of the total. Each stage is a temporary structure designed to hold fuel and engines long enough to accelerate the remaining mass. When empty, it becomes unnecessary weight and is discarded. The architecture resembles a ladder built from fire, each rung consumed in sequence to lift what remains. Reusable systems alter the economics of spaceflight, yet they do not alter the physics. Recovering boosters requires reserving additional propellant for descent and landing burns, which in turn reduces the mass available for payload or demands larger initial capacity. The energy required to reach orbit remains governed by gravity and orbital mechanics, indifferent to engineering elegance. Chemical rockets rely on the energy stored in molecular bonds, and there are limits to how much energy those bonds can release. Improvements in materials and guidance refine efficiency, but they do not erase the fundamental cost of climbing out of a gravitational well this deep. To depart entirely, to commit to translunar injection or beyond, additional velocity must be added once orbit is achieved. The spacecraft must accelerate again, stacking energy upon energy until its trajectory stretches outward. Each increment is purchased with propellant mass carried from the ground. Thus, every kilogram launched carries within it the burden of the fuel required to lift it, and the fuel required to lift that fuel. The ascent from Earth is therefore not a simple departure, but a layered expenditure, a sustained exchange between stored chemical potential and the persistent curvature of a planet that does not easily let go. It rose from the flat horizon like a white column carved against the sky, its proportions almost architectural in their clarity. The Saturn V stood 110 meters tall, a structure less like a vehicle and more like a temporary monument assembled for a singular task. At launch, it weighed roughly 3,000 tons, most of that mass propellant held within stages stacked with deliberate symmetry. It was conceived in an era when urgency shaped engineering, when national focus condensed around a fixed objective and resources flowed with unusual concentration. Every line of its design pointed in one direction, outward toward the moon. The first stage alone contained 5 F1 engines arranged in a quincunx pattern, each engine among the most powerful single-chamber, liquid-fueled engines ever flown. Their combined thrust exceeded 34 million newtons at liftoff, enough to lift the immense vehicle slowly from the pad before acceleration built steadily. The combustion chambers consumed refined kerosene and liquid oxygen in torrents measured in tons per second, converting chemical energy into sustained force. Above that stage, liquid hydrogen-fueled engines continued the ascent, each level discarded once its propellant was exhausted. The architecture followed a clear philosophy: expend what is necessary to achieve translunar velocity. Preserve only the small command and service modules that would carry crew onward. This vehicle was not designed for routine access to orbit. It was not optimized for cost efficiency or rapid turnaround. It existed to deliver a specific payload beyond Earth to enable a sequence of maneuvers culminating in lunar orbit insertion and surface descent. During the height of the Cold War, funding levels for the Apollo program reached nearly 4% of the United States federal budget. Hundreds of thousands of engineers, technicians, machinists, and administrators contributed to a coordinated effort that treated the moon landing as a geopolitical imperative. Production lines for engines, stages, and guidance systems operated within that focused framework. The F1 engines themselves required manufacturing capabilities that pushed metallurgy and turbomachinery to their limits. Each unit underwent extensive testing, including static firings that shook facilities built solely for that purpose. After Apollo concluded, those industrial ecosystems dissolved gradually. Tooling was dismantled, suppliers shifted priorities, and the expertise dispersed into other sectors. Today, while detailed documentation survives and modern analysis could reconstruct similar engines, the original production infrastructure no longer exists. Recreating it would involve not only technical replication, but economic justification within a different strategic landscape. Modern launch vehicles reflect altered priorities. Reusability shapes their architecture, emphasizing recovery and refurbishment over single mission performance. Engines are often designed for multiple firings, with materials chosen to endure thermal cycles rather than maximize peak thrust for one ascent. Digital control systems allow fine-tuning of mixture ratios and throttling profiles, improving efficiency and operational flexibility. Yet, these refinements also distribute capability across varied mission classes, from satellite deployment to cargo resupply and planetary probes. The Saturn V represented concentration, a convergence of funding, political will, and engineering toward a solitary objective. Its scale matched the clarity of that aim. Contemporary systems balance broader portfolios, serving commercial markets, scientific research, and human exploration simultaneously. The result is a fleet shaped by adaptability rather than singular purpose. In the quiet archives of aerospace history, the Saturn V remains a testament to what focused intent can assemble. A vehicle built not for repetition, but for arrival, constructed to expend itself in the act of reaching another world. In the early 1960s, the moon was not only a destination, but a deadline. The effort that formed around it did not resemble a typical research initiative unfolding at a measured pace. It carried the tempo of urgency, shaped by rivalry that extended far beyond laboratories and launch facilities. When Apollo reached its peak, NASA consumed roughly 4% of the United States federal budget, a proportion difficult to imagine in quieter decades. Resources flowed with unusual continuity, insulated from short-term hesitation by a political consensus that framed lunar arrival as a matter of national stature. More than 400,000 people contributed to that momentum. Engineers refined guidance algorithms. Machinists shaped components to tolerances measured in thousandths of an inch. Mathematicians translated orbital mechanics into sequences of executable steps. Seamstresses stitched pressure garments with patient precision. Universities, private contractors, and government centers formed an interlocking network that operated with singular focus. The scale of coordination required new management techniques, including systems engineering practices that linked subsystems into a coherent whole. Apollo became less a program than an ecosystem, sustained by an atmosphere of collective concentration. The geopolitical context intensified every milestone. The launch of Sputnik had demonstrated capability in orbit, and subsequent achievements by the Soviet Union underscored the strategic symbolism of space. Within that climate, the commitment to land humans on the moon before the decade's end carried implications beyond exploration. Success would signal technological leadership, failure would echo globally. This framing influenced decision-making at every level. Timelines were compressed, parallel development paths were pursued, manufacturing proceeded while testing continued. Risk was not ignored, but it was weighed against urgency with a different calculus than would later prevail. Safety standards evolved through experience, yet they reflected the era's tolerance for uncertainty. Redundancy existed, and contingency procedures were detailed, but margins were often narrow. The tragic fire during a ground test of Apollo 1 revealed vulnerabilities that prompted redesigns and deeper scrutiny. Even so, the broader culture accepted that human spaceflight involved inherent peril. Astronauts trained with the understanding that exploration carried personal risk, and public sentiment, shaped by the Cold War narrative, supported continued effort despite setbacks. Financial commitment enabled hardware to be built specifically for lunar missions without immediate concern for reuse or commercial return. Facilities were constructed at unprecedented scale. Test stands rose to accommodate engines of extraordinary thrust, assembly buildings, enclosed vehicles of monumental height. When objectives were achieved and geopolitical pressures shifted, sustaining that level of expenditure proved less feasible. The budget fraction devoted to space declined, and priorities diversified across scientific, military, and domestic domains. Apollo's intensity cannot be separated from its context. It was born from a convergence of competition, ambition, and concentrated funding that allowed complexity to be absorbed within a relatively brief span. The program advanced technology in guidance, computers, materials, science, and propulsion, yet it did so within a framework that tolerated compressed schedules and elevated risk. In later decades, as exploration goals broadened and public accountability deepened, the environment surrounding human spaceflight changed. Apollo remains an example of what focused national will can assemble, but it also reflects a moment when urgency shaped decisions in ways that differ from the slower, more distributed efforts that define contemporary return to deep space. In contemporary launch control rooms, silence carries a different weight than it once did. Rows of monitors glow softly, each screen tracing parameters that must remain within carefully defined limits. Before a human being is cleared to board a rocket, layers of verification unfold quietly across years of design and testing. The phrase human-rated is not ceremonial. It signals that every critical system has been examined for failure modes, cross-checked against independent analyses, and reinforced with redundancy where possible. A single string of electronics is rarely trusted alone. Parallel circuits, backup computers, and duplicate sensors stand ready to assume control if primary pathways falter. Redundancy shapes the architecture from the earliest sketches. Structural components are evaluated for load margins beyond expected stresses. Propulsion systems are instrumented to detect minute deviations in pressure or temperature. Software is subjected to simulations that inject faults deliberately, observing how algorithms respond under strain. Each potential weakness is cataloged and traced through review boards composed of specialists who examine not only whether a component works, but how it might fail. The process is iterative and deliberate, sometimes stretching schedules as new data emerges. Abort capability occupies a central place in modern crewed spacecraft. Launch escape systems are designed to activate within fractions of a second, pulling a capsule away from an exploding booster if necessary. These systems must function at multiple points during ascent, when aerodynamic forces and dynamic pressures vary dramatically. Engineers model scenarios in which engines shut down unexpectedly or guidance drifts outside tolerance. Hardware is tested to ensure separation motors ignite reliably, parachutes deploy in sequence, and landing systems cushion impact within survivable limits. The goal is not merely to reach orbit, but to provide a path home at nearly every phase of flight. Such caution reflects experience accumulated over decades. Tragedies in both American and international programs have reshaped standards, embedding lessons into procedural frameworks. Independent safety offices hold authority to halt launches if concerns arise. Documentation trails accompany every component, recording manufacturing history, inspections, and modifications. Certification requires consensus across disciplines, from materials science to avionics. This culture values transparency and accountability, recognizing that public trust rests on demonstrable diligence. Engineering review cycles have lengthened as systems grow more complex. Modern vehicles integrate advanced composites, digital fly-by-wire controls, and autonomous navigation capabilities. Each innovation introduces interactions that must be understood comprehensively. Computational models assist, yet they are validated against physical testing to ensure assumptions align with reality. Ground tests replicate vibration, thermal extremes, and vacuum conditions as closely as feasible. When anomalies appear, investigations proceed methodically, sometimes redesigning subsystems to eliminate ambiguity. Public perception has also evolved. Human spaceflight remains inspiring, but tolerance for preventable loss has narrowed. Media scrutiny is immediate and global. Decisions are dissected in real time. Agencies and companies operate within societies that expect rigorous risk, mitigation, and ethical responsibility. This environment encourages conservatism in timelines and incremental progression in capability. Missions are postponed rather than rushed, components replaced rather than accepted with uncertainty. The cumulative effect of stricter standards is not hesitation but refinement. Progress continues, guided by a philosophy that treats human life as the central constraint around which all engineering must conform. Launches may occur less frequently, schedules may extend beyond initial projections, yet each delay often represents an unseen layer of assurance added quietly to the structure. In this measured approach, ambition persists, tempered by a collective commitment to return crews safely through every stage of the journey. In the quiet geometry of spaceflight, direction is never a straight line, but a curve shaped by gravity. Once a spacecraft has settled into orbit around Earth, circling with balanced velocity, the path toward the moon begins not with a turn of the nose, but with a deliberate increase in speed. This maneuver, Known as translunar injection, is a carefully timed burn that lengthens the orbit into an ellipse whose farthest point reaches outward toward lunar distance. Engines ignite for minutes that feel longer than their duration, adding just enough velocity to allow Earth's hold to loosen at the precise angle required. The burn must occur at an exact position along the orbital path. Too early or too late, and the resulting trajectory drifts off alignment. Guidance systems calculate the required delta V, the incremental change in velocity measured in meters per second, with extraordinary precision. Propellant flows through valves and turbopumps respond instantly to commands, while onboard computers adjust thrust vectors to maintain stability. When the engines fall silent, the spacecraft does not head directly toward the moon as if aimed along a straight corridor. Instead, it begins a long arc, climbing gradually away from Earth under diminishing gravitational influence. The coast that follows extends for roughly 3 days. During this time, motion appears almost serene, yet the mathematics governing it remains exacting. Earth's gravity continues to shape the trajectory, even as lunar gravity begins to assert a subtle pull. The spacecraft travels through a region where forces from both bodies interact, and tiny deviations can grow quietly over distance. A misalignment of a fraction of a degree at departure can translate into thousands of kilometers at arrival. For this reason, mid-course correction burns are planned, brief firings that trim the path with gentle adjustments. As the vehicle approaches the moon, relative velocity must be managed carefully. Arriving too fast would carry it past lunar orbit into solar trajectory. Arriving too slow would allow the moon's gravity to alter the path unpredictably. Lunar orbit insertion requires another precise burn, executed at the moment when the spacecraft passes behind the moon from Earth's perspective. Engines fire retrograde, reducing velocity so that the craft becomes bound to the moon rather than slipping by. Timing is critical, since the window for effective insertion is narrow and dependent on both position and speed. The compounding nature of orbital mechanics leaves little room for approximation. Navigation relies on tracking data from Earth-based antennas and onboard star trackers that compare celestial positions against internal catalogs. Each measurement refines the estimate of position and velocity. Corrections are small by terrestrial standards, often measured in meters per second, yet they determine whether the spacecraft enters a stable orbit or drifts into an unintended path. Gravity assists, sphere of influence, transitions, and three-body dynamics all play roles in shaping the journey. From a distance, the movement appears graceful, an elegant sweep from one world to another. Beneath that grace lies a lattice of calculations that must remain coherent over hundreds of thousands of kilometers. The physics does not bend for aspiration. It responds only to velocity, mass, and time. Translunar travel, therefore, becomes an exercise in accumulated precision, where each burn sets conditions for the next, and each correction preserves alignment across a vast and quiet expanse shaped entirely by motion and gravity. Approaching the lunar surface, a spacecraft finds no haze softening the horizon, no blue gradient fading into black. The boundary between space and ground is abrupt because there is no atmosphere to mediate the transition. On Earth, returning vehicles rely on air as both shield and brake. Friction converts kinetic energy into heat. Lift can be generated by shaping surfaces against flowing molecules. The moon offers none of this. Its exosphere is so tenuous that it provides no meaningful resistance. A vehicle descending toward the surface encounters vacuum until the final meters above regolith. Without air, Aerodynamic braking is impossible. There are no shock waves to build gradually, no parachutes to deploy, no wings to angle for glide. Every change in velocity must be produced by onboard propulsion. Descent becomes an exercise in subtracting speed through controlled thrust, counteracting gravity entirely with engine output. The spacecraft must arrive in lunar orbit with enough propellant reserved not only for landing, but for hovering, adjusting, and correcting as the surface approaches. Lunar gravity is approximately one-sixth that of Earth, yet it remains sufficient to accelerate a falling object steadily. A lander begins its descent by lowering its orbit, reducing horizontal velocity while allowing altitude to decrease. At a calculated point, the engines rotate the vehicle from a forward-facing orientation into a nearly vertical posture. Thrust then increases to oppose the downward acceleration. Unlike atmospheric entry on Earth, where the environment participates in slowing the craft, the lunar landing is powered from start to finish. This dependence on propulsion creates a narrow margin for error. If an engine underperforms or fails, there is no surrounding medium to compensate. Redundancy can be built into systems, and throttleable engines allow fine control of descent rate, but the physics remain unforgiving. The lander must modulate thrust precisely to avoid both excessive descent speed and excessive fuel consumption. Burning too aggressively risks running out of propellant before touchdown. Burning too conservatively risks a hard impact. As the surface draws near, visibility presents another challenge. Engine exhaust strikes the regolith and lofts fine dust outward in expanding sheets. With no atmosphere to carry particles upward in plumes, the dust travels along ballistic arcs, obscuring landmarks and altering surface appearance. Optical sensors must distinguish terrain through shifting patterns of light and shadow. Radar altimeters provide range data, translating distance into signals that guide final adjustments. The last moments of descent unfold within a narrow corridor of acceptable velocities measured in meters per second. Because there is no aerodynamic glide path, abort options are limited during the final phase. A return to orbit requires sufficient propellant and structural integrity to reorient and accelerate upward. The window for such a maneuver closes rapidly as fuel diminishes. Mission planners, therefore, design landing sequences with conservative margins, accounting for uncertainties in mass, engine performance, and surface conditions. Each kilogram allocated to descent propulsion represents a balance between safety and payload capacity. The absence of atmosphere simplifies some aspects of engineering by eliminating concerns about wind or weather, yet it transfers responsibility entirely to the spacecraft. The lander must carry within itself every means of slowing, stabilizing, and settling onto the surface. In that airless environment, gravity and momentum interact without interference, and the path from orbit to ground becomes a continuous act of controlled thrust, sustained until the final contact with a landscape that offers no cushioning beyond the strength of engineered systems. Descent toward the lunar surface unfolds not as a gentle settling, but as a deliberate surrender to gravity moderated by fire. Once a lander commits to leaving orbit, it begins to fall, though the word fall carries a quiet precision here. Lunar gravity, roughly one-sixth that of Earth's, draws the vehicle downward with steady acceleration. The pull is weaker than at home, yet it is constant, and without intervention it would carry the craft to the ground at destructive speed. Landing, therefore, becomes the art of shaping that fall into something survivable, a balance between downward motion and upward thrust. The trajectory begins with horizontal velocity. Inherited from orbit, engines ignite to reduce that sideways motion, allowing altitude to decrease. As the surface rises in the windows or on instrument displays, the lander pitches upright. From that moment onward, thrust must nearly equal the force of gravity, trimming descent rate to meters per second rather than hundreds. Throttleable engines respond to subtle adjustments, increasing or decreasing output in increments that determine whether the craft steadies or accelerates. Unlike atmospheric descent on Earth, there is no drag to provide passive resistance. Every correction must come from combustion. Fuel margins define the emotional geometry of the maneuver, even if those aboard speak in numbers rather than feelings. The Apollo landers carried limited propellant reserves for the final approach. Mission planners calculated expected consumption with care, yet variations in terrain and guidance required flexibility. As Neil Armstrong guided Eagle toward a safer landing site, onboard readouts counted down remaining seconds of burn time. That constraint was not unusual. It was embedded in the architecture. Carrying excess fuel would have required a larger ascent stage, which in turn would have demanded greater launch mass from Earth. The system was optimized for arrival, not comfort. Dust introduces another layer of complexity. When descent engines direct exhaust toward the surface, they disturb the regolith into expanding sheets of fine particles. With no atmosphere to disperse them gradually, the grains travel along ballistic paths, skimming outward and upward before settling again. During the final meters, this dust can obscure visual cues, softening shadows and masking small hazards. Pilots rely on radar altimeters and inertial measurement units to supplement what eyes cannot clearly resolve. The surface beneath becomes a shifting pattern of light and motion, requiring steady interpretation. Controlled falling demands synchronization between guidance software and human judgment. The computer calculates descent rate and attitude adjustments, yet the crew monitors performance, ready to intervene if readings diverge from expectation. Throttle commands translate into changes in chamber pressure and thrust within fractions of a second. The balance is dynamic. Too much thrust, and the lander may rise unexpectedly, consuming precious fuel. Too little, and the descent rate increases beyond tolerance. The margin narrows as propellant mass decreases, altering the vehicle's response to the same engine output. In the final moments, contact probes extend from the landing legs, designed to sense the surface just before touchdown. When they register contact, engines are cut to prevent tipping from lingering thrust. The vehicle settles onto pads engineered to absorb the remaining kinetic energy. The fall has been guided, slowed, and shaped, yet it remains fundamentally a fall, governed by gravity that does not negotiate. Successful landing emerges from the disciplined modulation of that inevitability, transforming descent into arrival through precision, sustained until motion resolves into stillness. Across the lunar plains lies a surface that appears soft from a distance, pale and powdery beneath unfiltered sunlight. Yet this layer, known as regolith, is the product of billions of years of relentless micrometeorite impacts. With no atmosphere to slow incoming fragments, even grains of cosmic debris strike at high velocity, fracturing rock into ever finer particles. Each impact shatters, melts, and fuses material in a cycle repeated across geological time. The result is not soil shaped by wind or water, but a complex mixture of crushed basalt, glassy shards, and mineral fragments formed in vacuum. Under magnification, these particles reveal edges that are angular and irregular. On Earth, erosion rounds grains into smoother forms, their corners softened by water and air. The Moon offers no such moderation. Regolith retains the sharpness of fracture, surfaces jagged at microscopic scales. When astronauts walked across the terrain during Apollo, their boots disturbed this powder, lifting it into brief arcs before it settled again. Without atmospheric drag, the dust did not drift gently but followed ballistic paths, spreading outward in thin veils before falling back. Static electricity further complicates its behavior. Ultraviolet radiation from the sun charges the surface, creating electric fields that cause fine particles to cling persistently to fabric and metal. During Apollo missions, dust adhered to spacesuits, tools, and equipment with surprising tenacity. It accumulated in folds and seams, coating visors and obscuring markings. Once inside the lunar module, particles floated briefly in the cabin before settling, carrying with them the abrasive character of their fractured edges. This abrasiveness presented mechanical challenges. Seals and joints designed to flex and rotate encountered grit that wore at surfaces with repeated movement. Zippers became difficult to operate. Hinges resisted motion. Although missions were brief, engineers noted the cumulative effects and considered implications for longer stays. Dust infiltrating bearings or airlocks could degrade performance over time, compromising systems that must operate reliably in isolation. Health considerations emerged as well. Lunar regolith contains fine particles small enough to be inhaled if introduced into a pressurized habitat. Laboratory analyses of returned samples suggested that prolonged exposure could irritate lung tissue as sharp fragments interact with delicate membranes. The absence of weathering processes means reactive surfaces remain chemically active, potentially generating oxidative stress when in contact with biological systems. While Apollo crews experienced only short-term exposure, extended habitation would require mitigation strategies to limit contamination. Modern mission planners study these characteristics closely. Concepts for future landers and habitats incorporate dust-resistant coatings, improved filtration systems, and airlock designs that isolate suits externally. Robotic precursors test how regolith behaves under repeated engine exhaust, wheel traction, and mechanical manipulation. The aim is not to eliminate dust, which is inseparable from the lunar surface, but to understand and manage its influence. In photographs, the moon appears serene, its surface smooth under stark illumination. Yet at ground level, regolith reveals a different texture, shaped by impacts, too small to leave visible craters, but persistent enough to grind rock into powder. It is a reminder that even in stillness, the lunar environment carries subtle hazards. The dust does not roar or blaze. It settles quietly on equipment and fabric, accumulating grain by grain, its sharpness preserved across ages in the airless calm. On the lunar surface, time unfolds at a different rhythm. A single day, measured from one sunrise to the next, lasts roughly 14 Earth days, followed by an equally long night. Without an atmosphere to scatter light or distribute heat, illumination arrives unfiltered and departs without lingering warmth. When the sun rises above the horizon, its radiation falls directly onto regolith and metal alike, unsoftened by clouds or air. Temperatures climb steadily, reaching approximately plus 127 degrees Celsius in exposed regions. Shadows cast sharply against the ground remain stark and cold by contrast, since there is no air to carry warmth sideways. As the long daylight continues, surfaces absorb energy until thermal equilibrium settles at extremes that challenge conventional materials. Metal components expand, lubricants thin or evaporate. Seals experience differential stress as one side of a structure faces sunlight, while another remains shaded. Thermal gradients develop across relatively small distances, forcing engineers to account for expansion and contraction cycles that repeat with each lunar rotation. Radiators and insulation become as vital as propulsion, shaping the internal environment where instruments and crews must function. When the sun finally dips below the horizon, The transformation is swift. With no atmospheric blanket to retain heat, energy radiates back into space. Temperatures descend toward minus 173 degrees Celsius during the extended night. Equipment that endured searing daylight must now withstand intense cold. Materials contract. Batteries lose efficiency. Brittle components risk fracture if not properly conditioned. Electronics, designed for stable terrestrial climates, require thermal control systems to maintain operational ranges within narrow tolerances. Spacecraft and habitats address these extremes through layered strategies. Multi-layer insulation, composed of reflective foils separated by vacuum gaps, reduces radiative exchange. Heaters, powered by stored energy or radioisotope sources, provide warmth during darkness. Thermal louvers regulate the release of internal heat during daylight, preventing overheating. Designers model not only average conditions but peak fluctuations, anticipating how surfaces oriented differently toward the sun will respond. The absence of convective cooling means that heat cannot simply drift away. It must be conducted through structures or radiated deliberately into space. The extended duration of lunar day and night introduces logistical considerations as well. Solar arrays generate abundant power during illumination, yet they fall silent for roughly 2 weeks when darkness prevails. Energy storage systems must bridge that interval, whether through high-capacity batteries or alternative power sources. Thermal inertia becomes both asset and challenge, as massive components retain heat longer but also require more energy to stabilize. Instruments placed within shadowed craters may remain perpetually cold, while those on elevated ridges experience dramatic cycling. These oscillations influence not only hardware but operational planning. Activities sensitive to temperature may be scheduled during moderate phases near sunrise or sunset. Mobility systems must account for traction changes as regolith responds subtly to heating and cooling. Even communication equipment can drift in frequency as components expand or contract, necessitating calibration. In the airless stillness, temperature is governed solely by radiation and conduction, without the moderating presence of wind or weather. The lunar surface becomes a landscape of thermal contrast, where survival depends on engineering that anticipates both blazing sunlight and prolonged darkness. Between these extremes, machines and habitats must maintain their own narrow climates, sustaining function through cycles that stretch across weeks in a realm where warmth and cold follow the sun without mercy or relief. When the sun slips below the jagged horizon of the moon, it does not return the next morning. Darkness extends across the surface for roughly 2 Earth weeks, a span long enough for warmth to dissipate completely. There is no twilight in the way it is known on Earth, no lingering glow scattered through air. Light withdraws sharply, and the terrain settles into a stark contrast of shadow and starlight. In that prolonged absence of illumination, systems designed for brief eclipses must endure an interval measured in hundreds of hours. Solar panels, which during daylight convert intense radiation into abundant electrical power, fall silent. Their cells, oriented carefully toward the sun during the long day, now face a sky that offers only distant stars. Without photons striking their surfaces, current ceases. For missions dependent on solar generation, this transition marks a fundamental shift. Energy must have been stored in advance, accumulated during the illuminated period, and preserved with minimal loss. The scale of storage required grows with the duration of night, since consumption continues even as production stops. Batteries become reservoirs of continuity. Lithium-ion chemistries, common in modern spacecraft, must be protected from the deep cold that accompanies darkness. As temperatures fall, internal resistance rises and capacity diminishes. Engineers encase battery packs within insulated compartments, sometimes supplementing them with heaters powered by the very energy they safeguard. The balance is delicate, since drawing power to maintain temperature reduces the reserve available for other functions. Each subsystem, from communication arrays to life support processors, draws from the same finite store. Thermal survival extends beyond electronics. Structural materials contract as heat radiates into space. Interfaces between different materials experience stress due to varying coefficients of expansion. Lubricants can thicken or solidify, impeding mechanical movement. Instruments calibrated for stable internal conditions rely on active thermal control to prevent drift. In habitats designed for human presence, maintaining a livable interior becomes a sustained effort, requiring insulation that limits heat loss and heating elements that offset radiation into vacuum. Some mission concepts explore alternative power sources to bridge the lunar night. Radioisotope thermoelectric generators provide steady output independent of sunlight, converting heat from radioactive decay into electricity. Nuclear fission reactors, scaled for surface deployment, are studied as means to supply continuous power through both day and night cycles. These approaches introduce additional engineering and regulatory considerations, yet they offer resilience against the extended darkness inherent to the moon's slow rotation. The long night also influences operational tempo. Activities that demand high energy input may be scheduled during daylight when generation is abundant, while the night period emphasizes conservation and monitoring. Robotic explorers designed to survive the darkness often enter low power states, shutting down non essential systems to preserve charge. Upon sunrise, gradual rewarming precedes full reactivation, ensuring that components reach safe operating temperatures before demanding loads resume. In this environment, survival is measured not in hours, but in weeks. The absence of sunlight is not merely a visual change, but an energetic constraint that shapes architecture and planning. Where Earth offers alternating cycles within a single day, the Moon extends each phase into a prolonged chapter. During the long night, machines and habitats must rely entirely on foresight, insulation, and stored energy, sustaining function through a quiet interval when the landscape rests in cold and the horizon remains dark until the sun begins its slow return. Above the lunar surface, there is no protective dome, no invisible field bending charged particles aside. The moon possesses no global magnetic field comparable to Earth's, and it holds no substantial atmosphere to absorb incoming radiation. Space presses directly against regolith and metal alike. In this environment, energy that would be deflected or scattered at home arrives with little interference, moving through vacuum until it meets whatever structure stands exposed. Radiation in deep space is not uniform. It arrives from multiple sources, each with distinct character. Galactic cosmic rays originate far beyond the solar system, accelerated by supernova remnants and other energetic phenomena. These particles, often atomic nuclei stripped of electrons, travel at velocities approaching the speed of light. When they strike material, they can penetrate deeply, depositing energy along their paths and generating secondary cascades within shielding. Their flux is relatively constant, forming a persistent background that bathes the lunar surface day and night. Solar particle events introduce another dimension. The sun, though steady in its illumination, occasionally releases bursts of high-energy protons and heavier ions during flares and coronal mass ejections. These events can intensify radiation levels dramatically over short periods. On Earth, the magnetic field channels many of these particles toward polar regions, and the atmosphere absorbs much of their energy before it reaches the ground. On the Moon, there is no such buffer. A habitat or spacecraft must rely entirely on its own shielding and forecasting to mitigate exposure during these intervals. Shielding strategies revolve around mass and composition. Materials rich in hydrogen, such as water or specialized polymers, are effective at slowing high-energy particles. Lunar regolith itself can serve as protective cover if piled over habitats, using local material to add depth between occupants and space. Designers evaluate trade-offs between added mass and launch cost, balancing protection against feasibility. Even with substantial shielding, some radiation will pass through, interacting with electronics and biological tissue. For human crews, cumulative dose becomes a central consideration. Radiation can damage DNA, increasing long-term cancer risk and potentially affecting the nervous system. Short-term exposure during intense solar events may produce acute symptoms if shielding is insufficient. Monitoring instruments measure dose rates continuously, allowing mission control and crew to adjust operations or seek shelter within more heavily shielded compartments. The architecture of future lunar bases often includes designated storm shelters, areas reinforced with additional material where occupants can remain during periods of elevated flux. Electronic systems are equally vulnerable. High-energy particles can induce single-event upsets, flipping bits in memory or causing transient faults in processors. Hardened components and error-correcting codes reduce susceptibility, yet complete immunity is unattainable. Designers incorporate redundancy and fault detection to maintain reliability despite an environment that steadily challenges circuitry at microscopic scales. The absence of magnetic and atmospheric protection transforms the lunar surface into a place where radiation is not an occasional hazard, but a continuous presence. It does not announce itself with sound or visible light. It moves silently through structures, interacting at atomic levels. Managing this exposure requires anticipation rather than reaction, integrating shielding, monitoring, and operational planning into every aspect of sustained presence. In the stillness of the moon, where nothing shields the sky, survival depends on creating an artificial refuge against particles that have traveled across vast distances to arrive unimpeded at the surface. High above the lunar surface, space is not empty in the way it appears. It is threaded with fragments, grains of rock and metal, left over from the formation of the solar system, drifting in silent orbits around the sun. Some are no larger than sand, others smaller than dust motes, yet they travel at velocities measured in kilometers per second. When such particles intersect the moon's path, nothing slows them. There is no atmosphere to heat them into streaks of light, no friction to break them apart before arrival. They strike directly, transferring energy in abrupt flashes too small and too brief to witness from afar. Over billions of years, this steady rain of micrometeorites has reshaped the lunar surface. It has fractured rock into regolith, softened crater edges, and embedded tiny glass beads within the soil. The same process continues today, though individual impacts are rarely dramatic. A grain traveling at hypervelocity carries kinetic energy far beyond what its size suggests. Upon collision, it can vaporize itself and a small volume of target material, leaving a minute pit etched into rock or metal. Scaled across centuries, these events become a persistent environmental factor. For short missions, the statistical likelihood of a damaging strike remains low, yet it is never zero. Spacecraft hulls are engineered to withstand micrometeoroid impacts through layered shielding. Whipple shields, for example, use thin outer layers designed to fragment incoming particles before they reach the primary pressure vessel. The fragments disperse, spreading their energy over a wider area, reducing the chance of penetration. Even so, design margins must account for a spectrum of particle sizes and velocities, each contributing to cumulative risk. Habitats intended for extended occupation face a more complex equation. The longer a structure remains exposed, the greater the probability that a particle of sufficient energy will encounter it. A puncture need not be large to present a hazard in vacuum. Even a small breach can allow atmosphere to escape, requiring rapid detection and response. Monitoring systems measure pressure continuously, alerting occupants to deviations that might indicate impact damage. Repair kits and redundant compartments provide resilience, yet they add mass and complexity to the architecture. The absence of atmospheric shielding also affects equipment deployed on the surface. Solar panels, radiators, and communication antennas present broad surfaces to space. Over time, micrometeorite impacts can degrade their efficiency, pitting coatings and altering reflectivity. Designers evaluate expected flux rates based on observational data and lunar orbit measurements, incorporating protective layers where feasible. In some concepts, habitats are partially buried beneath regolith, using local material as both radiation and impact shielding. Robotic missions have provided insight into this environment. Detectors carried on lunar orbiters and landers record impact frequencies, refining models that predict exposure over years rather than days. These data inform planning for sustained presence, where maintenance schedules and structural reinforcement must consider not only immediate hazards but gradual wear from countless tiny collisions. The moon endures this continual bombardment without atmosphere to announce it. Each impact is a brief exchange of momentum and energy, adding another microscopic mark to a landscape already shaped by time. For those who would remain there longer than a fleeting visit, the challenge lies in acknowledging that even the smallest travelers of space carry consequences, and that structures built for permanence must be prepared to withstand a steady, invisible rain that never truly ceases. Between Earth and the Moon, silence is not empty but measured. Messages do not travel instantly across that span. They move at the speed of light, which, though immense, is finite. A signal requires a little over 1 second to cross the distance one way, and more than 2 seconds to complete a round trip. In everyday conversation, such pauses might feel negligible, yet in the context of spacecraft control, they alter the rhythm of interaction. Commands sent from Earth arrive after a delay, and confirmation returns only after another interval has passed. The exchange is no longer fluid, but staggered, each instruction separated from its consequence by the steady pace of physics. For robotic operations on the lunar surface, this delay complicates direct control. A rover responding to terrain obstacles cannot rely on instantaneous correction from controllers on Earth. By the time a command arrives and a response is observed, conditions may already have changed. Engineers therefore design systems with increasing autonomy, enabling onboard computers to interpret sensor data and make immediate decisions within defined parameters. Human oversight remains central, yet it shifts toward supervisory guidance rather than continuous steering. The geometry of the moon introduces additional complexity. The hemisphere facing Earth maintains line-of-sight communication, allowing radio waves to travel directly between surface and ground stations. The far side, however, remains permanently hidden from direct contact due to tidal locking. Any mission operating there must depend on intermediary platforms positioned in lunar orbit. Relay satellites occupy carefully chosen trajectories, maintaining visibility with both Earth and surface assets, forwarding signals across the obstructed horizon. Their orbits must be stable and predictable, since communication gaps could isolate equipment or crews at critical moments. Navigation relies on precise tracking of position and velocity, yet signal delay and limited vantage points introduce uncertainty. Ground-based antennas measure Doppler shifts and ranging data, calculating spacecraft trajectories with high accuracy. Still, as vehicles maneuver around the moon, periods of occlusion occur when direct tracking is unavailable. During these intervals, onboard inertial measurement units and star trackers sustain awareness of orientation and motion. Small errors can accumulate, necessitating periodic updates once communication resumes. The lunar environment lacks the dense network of satellites that supports global positioning on Earth. There is no comprehensive GPS constellation encircling the moon. Proposals for lunar navigation networks are under development, envisioning orbiters that broadcast timing signals to surface users. Until such systems mature, missions rely on a combination of Earth-based tracking, onboard computation, and, when available, relay infrastructure. Establishing and maintaining these links becomes an integral part of mission architecture rather than a peripheral consideration. For human explorers, communication constraints shape daily routine. Conversations with Earth proceed with subtle pauses, requiring patience and structured exchanges. Emergency scenarios demand pre-planned protocols since immediate back and forth troubleshooting is impractical. Autonomy extends beyond machinery to crews themselves, who must operate with confidence during periods when guidance is momentarily out of reach. Across the quiet distance, information flows steadily but never instantly. Each transmission traces an arc through space, bending around the moon's bulk if relayed, arriving with predictable delay. In this measured cadence, exploration unfolds within the limits imposed by light speed and geometry, reminding those who venture outward that connection endures, though always mediated by distance. Inside any spacecraft or habitat, survival depends not on propulsion or navigation, but on the quiet circulation of air and water through unseen systems. Life support is less a single machine than a network of processes that must operate without interruption. On Earth, atmosphere and hydrosphere surround the body effortlessly, replenished by planetary cycles that unfold beyond awareness. On the moon, those cycles must be recreated artificially, confined within walls, measured in centimeters rather than kilometers. Oxygen generation forms the foundation of this closed environment. Tanks can store breathable gas for limited durations, yet sustained presence requires regeneration. Electrolysis systems split water into hydrogen and oxygen, using electrical energy to separate molecules that were once bound together. The liberated oxygen feeds the cabin atmosphere, while hydrogen may be vented or combined with carbon dioxide in chemical reactors to reclaim additional water. Each reaction is monitored carefully, since slight imbalances can alter pressure and composition within the habitat. Carbon dioxide scrubbing operates in parallel. As crew members exhale, carbon dioxide accumulates, and even modest increases in concentration can impair cognition and health. Chemical absorbents, such as lithium hydroxide or regenerative systems using molecular sieves, capture the gas from circulating air. In regenerative configurations, captured carbon dioxide is processed and the absorbent material restored for reuse. Fans move air continuously through filters and reactors, maintaining uniform distribution so that pockets of elevated concentration do not form. Water recycling extends the loop further. Every liter carried from Earth represents mass that demanded energy to lift beyond gravity. For longer missions, resupply cannot be the sole strategy. Condensed humidity from breath and perspiration is collected, filtered, and purified. Wastewater from hygiene and other uses passes through multi-stage treatment systems that remove particulates, organic compounds, and dissolved salts. Advanced units employ distillation under reduced pressure or membrane filtration to recover potable water with high efficiency. Even urine is processed in carefully engineered cycles, reclaiming moisture that would otherwise be lost. These subsystems interact in subtle ways. Electrolysis depends on water purity. Scrubbing efficiency affects cabin humidity. Temperature influences chemical reaction rates. Sensors distributed throughout the habitat measure pressure, partial pressures of gases, humidity, and trace contaminants. Control software adjusts valves, pump speeds, and heater settings to maintain stability. Redundancy is woven into critical pathways, since a single point of failure could compromise the entire environment. Backup pumps, parallel filters, and reserve tanks stand ready should primary units falter. Continuous operation is essential. Unlike propulsion systems that fire in discrete burns, life support cannot pause. Filters saturate gradually, seals experience wear, microbial growth must be managed within water lines. Maintenance schedules become part of daily routine, with crews inspecting, cleaning, and replacing components as needed. Consumables are tracked meticulously, their depletion rates informing mission planning and contingency reserves. In the stillness beyond Earth's atmosphere, a habitat becomes a microcosm sustained by chemistry and engineering. Air is circulated by fans rather than wind. Water moves through pipes rather than rivers. The boundary between interior and vacuum is defined by the reliability of these systems. Each breath depends on molecules, processed moments earlier by devices humming quietly in adjacent compartments. Life support, often unnoticed in its success, represents a continuous negotiation with isolation, sustaining human presence through cycles that must remain balanced hour after hour without interruption. On a launch manifest, food and water appear as numbers beside other cargo, measured in kilograms and carefully allocated among instruments and structural components. Yet beyond Earth, those numbers acquire a different weight. Every kilogram placed atop a rocket demands additional propellant to lift it from the surface, additional structural reinforcement to contain that propellant, and additional planning to ensure arrival at the intended destination. The arithmetic begins long before departure, in calculations that translate mass into energy and energy into cost. Water is both sustenance and system resource. It supports hydration, hygiene, and oxygen generation through electrolysis. For short missions, tanks filled on Earth can suffice, their contents rationed with precision. For extended stays, reliance on transported water becomes increasingly impractical. Each liter carried outward represents mass that must first climb through gravity and then travel onward across cislunar space. Even with recycling systems recovering a high percentage of usage, losses accumulate. Filters retain impurities. Small leaks occur. Consumables degrade. Over months, the deficit grows unless replenished. Food follows a similar trajectory. Prepackaged meals designed for microgravity or reduced gravity environments are optimized for caloric density and shelf stability. Dehydrated components reduce mass, requiring water for reconstitution upon use. Packaging itself contributes to weight, though engineers strive to minimize it while maintaining safety and preservation. For brief expeditions, provisioning can be calculated with margins for contingency. For permanent or semi permanent presence, continuous resupply from Earth imposes logistical constraints that extend beyond simple transport. Resupply opportunities are governed by orbital mechanics. Launch windows depend on alignment between Earth and Moon, as well as vehicle availability and weather conditions at departure sites. Delays can ripple through schedules, compressing margins for critical supplies. Storage capacity within habitats must account for variability, ensuring that essential resources remain sufficient even if a planned shipment slips. This requirement adds structural mass to provide volume and containment, reinforcing the cycle in which added capability demands added energy at launch. Cost is intertwined with physics. Chemical propulsion requires significant propellant to deliver cargo beyond low Earth orbit, and while reusable boosters reduce some expenses, the upper stages and deep space transfers remain energetically intensive. Each kilogram not only consumes fuel but influences trajectory design and payload configuration. Trade studies weigh scientific equipment against consumables, structural shielding against stored provisions. The balance shifts depending on mission, duration, and objectives. Sustainable presence on the Moon therefore invites consideration of local resources. Polar regions harbor water ice within permanently shadowed craters, detected by orbital instruments and neutron spectrometers. Extracting and processing this ice into usable water could reduce dependence on terrestrial shipments. In situ resource utilization concepts envision converting regolith into building materials or extracting oxygen bound within minerals. These approaches require machinery, power, and infrastructure, themselves launched from Earth, yet they offer the prospect of gradually decreasing the mass that must be transported over time. Food production presents a more complex challenge, involving controlled agriculture within enclosed environments. Experiments in plant growth under reduced gravity and artificial lighting explore possibilities for supplementing stored provisions. Such systems demand water, nutrients, and careful environmental control, intertwining with life support architecture. In the ledger of lunar habitation, mass remains a central constraint. Energy invested at launch echoes through every aspect of planning. To remain for weeks is feasible with careful provisioning. To remain for years requires shifting from import to utilization. The transition from visitor to resident is measured not only in days spent on the surface, but in kilograms that no longer need to cross the distance from Earth. Before a single habitat can shelter human presence, the ground itself must accept structure, and on the Moon, that acceptance is not passive. The surface bears no wind to erode foundations, no rain to seep into seams, no vegetation to encroach upon walls. At first glance, the absence of weather suggests stability, a landscape frozen in geological patience. Yet this same absence removes protection. There is no atmospheric buffer to soften radiation, no air to distribute heat, no shield against the steady arrival of micrometeorites. Any structure placed upon regolith stands directly within the full exposure of space. Because of these conditions, construction cannot begin with crews and manual tools. The first builders must be robotic. Machines capable of operating in vacuum and extreme temperatures will grade terrain, deploy landing pads, and assemble prefabricated modules before humans arrive. Tele-operated systems, guided from Earth or from orbiting stations, must function with high degrees of autonomy due to communication delays. Their movements will be deliberate, each action pre-planned and monitored, since repair options are limited until infrastructure expands. Regolith itself presents both opportunity and obstacle. Its fine particles can be sintered using focused energy, fused into solid blocks or landing surfaces that resist erosion from engine exhaust. Additive manufacturing techniques envision using local material as feedstock, reducing dependence on transported construction supplies. Yet the same dust that enables in situ resource utilization also infiltrates joints, bearings, and seals. Robotic arms manipulating tools must contend with abrasion that gradually degrades precision. Protective housings and wipers mitigate contamination, though they add complexity and mass. Lighting conditions further complicate operations. Without atmospheric scattering, illumination is harsh and directional. Surfaces in direct sunlight appear intensely bright, while adjacent shadows fall into deep darkness. Cameras and optical sensors struggle to maintain dynamic range across such contrast. Vision systems require advanced exposure control and image processing to distinguish terrain features reliably. In polar regions, where low solar angles persist, long shadows stretch across uneven ground, obscuring hazards and distorting perception. Autonomous navigation algorithms must interpret this environment accurately to avoid missteps. Thermal extremes influence materials selected for structural components. Metals and composites expand and contract across the extended day and night cycle, placing stress on joints and connections. Anchoring systems must account for regolith's granular properties, which differ from cohesive soils on Earth. Foundations may rely on compaction, sintering, or mechanical penetration to achieve stability. Engineers simulate these interactions in vacuum chambers and reduced gravity test facilities, yet full-scale validation can occur only on the surface itself. Logistics intertwine with engineering. Prefabricated modules launched from Earth must survive transit and landing before being integrated into a larger complex. Interfaces between modules demand precise alignment, sealing mechanisms that function despite dust contamination, and structural compatibility under varying thermal loads. Robotic assembly sequences must be choreographed carefully, since a misalignment could propagate delays until corrective missions are mounted. Building on the moon, therefore, becomes a layered undertaking, beginning with machines that prepare the site under conditions alien to terrestrial construction. Each bolt tightened and panel deployed must endure vacuum, radiation, and the quiet persistence of abrasive dust. The absence of weather does not simplify the task. It shifts the challenge toward exposure and precision. In this environment, permanence arises not from resisting storms, but from designing structures that coexist with unfiltered sunlight, deep shadow, and the steady stillness of an airless world. On modern launch pads, a new philosophy has taken shape, one that treats rockets not as single-use instruments, but as vehicles meant to return, land, and fly again. Tall, stainless steel prototypes rise with the promise of repetition, their engines engineered for multiple firings, and their structures reinforced to endure both ascent and descent. Starship, conceived as a fully reusable system, embodies this shift. Its boosters are intended to descend under controlled thrust, settling back onto terrestrial platforms rather than falling into the ocean. The vision suggests abundance through reuse, reducing cost per launch by spreading manufacturing effort across many flights. Yet, reusability addresses only part of the journey. Reaching low Earth orbit is one threshold. Departing from it toward the Moon demands additional velocity that must be supplied by propellant already in space. For a vehicle as large as Starship, the amount of fuel required for translunar injection and subsequent maneuvers exceeds what can be launched in a single ascent when also carrying cargo or crew. The architecture therefore includes orbital refueling, a choreography in which tanker variants launch separately, rendezvous in orbit, and transfer cryogenic propellants to a waiting spacecraft. Transferring supercooled liquids between vehicles in microgravity is a technical challenge still under active development. Liquid oxygen and liquid methane must remain within narrow temperature ranges to prevent excessive boil-off. In orbit, without gravity to settle fluids at the bottom of tanks, propellant management devices use screens, vanes, and controlled thrust to position liquids for transfer. Pumps and valves must operate reliably in vacuum and thermal extremes, ensuring that fuel moves efficiently without introducing bubbles that could disrupt engine performance. Demonstrations have begun, yet full-scale operational sequences require repeated validation. Each additional launch in a refueling chain introduces coordination demands. Tanker vehicles must reach orbit within defined time windows, align trajectories with the receiving spacecraft, and dock with precision. Orbital mechanics governs these rendezvous, and delays in one element can cascade through the sequence. Weather, ground operations, and vehicle readiness all influence timing. A mission to the Moon using this architecture may involve several launches in succession, each one a prerequisite for the next stage of departure. Cryogenic propellants present further considerations. Even with advanced insulation, some degree of boil-off occurs as heat leaks into tanks over time. Extended loiter in orbit increases losses, potentially requiring additional tanker flights to compensate. Engineers explore active cooling systems and sun shielding strategies to limit this effect, yet these solutions add mass and complexity. Reusability offers significant advantages in reducing manufacturing cost and enabling higher launch cadence. It allows vehicles to be inspected, refurbished, and improved iteratively. However, the physics of deep space travel remain unchanged. The energy required to depart Earth orbit and reach lunar distance must still be supplied, whether by a single expendable stage or by multiple reusable flights that aggregate propellant in orbit. The elegance of landing a booster upright does not eliminate the need for intricate coordination beyond the atmosphere. In this layered architecture, success depends not only on a single rocket performing flawlessly, but on a sequence of launches, dockings, and transfers unfolding without interruption. Reusability reshapes economics and operational philosophy, yet it coexists with orbital mechanics and thermodynamics that continue to set the boundaries within which exploration proceeds. In the architecture of modern lunar missions, orbit itself becomes a kind of staging harbor, a place where vehicles pause not to rest but to be filled. A single launch no longer carries all the energy required for departure beyond Earth. Instead, tanker flights rise separately, each one delivering a portion of propellant to a spacecraft already circling the planet. These tankers must reach matching orbital planes and altitudes, adjusting their paths through measured burns until rendezvous geometry aligns. What appears from the ground as independent launches becomes, in space, a tightly coordinated sequence. Once in proximity, docking operations begin. Precision is essential, since even small relative velocities can translate into significant structural loads. Guidance systems rely on radar, LiDAR, and optical tracking to refine alignment, while thrusters pulse in brief increments to nullify drift. Mechanical capture mechanisms extend and engage, forming a sealed interface between vehicles. The procedure resembles those practiced for space station resupply, yet the stakes are elevated by the nature of the cargo. Inside the tanks lie cryogenic propellants, liquid oxygen, and liquid methane cooled to temperatures far below freezing. Maintaining these fluids in orbit presents thermodynamic challenges. Even with multi-layer insulation and reflective sun shields, heat from sunlight and internal conduction gradually seeps inward. As temperature rises, a fraction of the propellant vaporizes, increasing tank pressure. Venting may be required to maintain structural limits, resulting in gradual loss. Engineers explore active cooling systems to reduce boil-off, but such systems draw power and add mass. Timing therefore becomes critical. The interval between tanker delivery and final departure must be managed to minimize waste. The transfer itself requires careful fluid management. In microgravity, liquids do not settle naturally at the bottom of tanks. Surface tension and small accelerations determine their distribution. To move propellant from one vehicle to another, pumps and pressure differentials are orchestrated alongside gentle thrusting that creates artificial settling. Valves open in sequence, and sensors monitor flow rates and temperatures to prevent cavitation or unintended mixing. The process must avoid introducing gas bubbles into feed lines that could impair engine ignition later. Each tanker flight represents a link in a chain that stretches from launch pad to translunar injection. Weather delays at the surface, minor anomalies during ascent, or issues encountered in orbit can shift schedules and propagate through the sequence. If a single tanker underperforms or fails to reach rendezvous, additional launches may be required, extending loiter time and increasing exposure to boil off. The choreography demands reliability not only from individual vehicles, but from the entire system operating in concert. Precision docking, thermal management, and fluid transfer converge in this orbital ballet. Success depends on repeated execution of complex maneuvers under the constraints of vacuum and microgravity. Unlike a single expendable stage carrying its fuel from liftoff, this distributed approach accumulates energy gradually, assembling the capacity for deep space travel piece by piece. When the final tanker disengages and the spacecraft's tanks are filled to the required level, the mission stands poised on the threshold of departure. Yet that readiness reflects the flawless performance of every preceding step, since the architecture allows little margin for cumulative error. High above the lunar surface, in an elongated orbit that carries it alternately close to the moon and far beyond it, a small station is planned to circle in quiet repetition. The lunar gateway is envisioned not as a destination in itself, but as an intermediate foothold, a node suspended between Earth and the surface below. Its orbit, known as a near rectilinear halo orbit, is shaped by the combined gravitational influence of Earth and Moon, allowing the station to remain relatively stable with modest propulsion for station keeping. From this vantage, it would see the lunar poles in recurring cycles while maintaining line of sight to Earth for communication. The concept introduces a new layer into the architecture of return. Rather than sending a single spacecraft directly from Earth orbit to the lunar surface and back, missions would unfold in stages. A crew vehicle would travel from Earth to Gateway, dock, and transfer astronauts and supplies. A separate lander, prepositioned or arriving independently, would then descend from the station's orbit to the surface. After completing surface operations, the lander would return to Gateway, where crew would reboard the transport vehicle for the journey home. Each segment offers flexibility, yet each also introduces additional coordination. Maintaining an orbiting station around the moon requires its own logistics. Modules must be launched, assembled, and supplied. Power systems, likely solar arrays, must generate electricity through the long cycles of light and shadow characteristic of the chosen orbit. Propulsion systems must execute periodic burns to preserve orbital stability against gravitational perturbations. Communication arrays must relay signals between surface explorers and Earth, supplementing other relay assets. The station becomes both a waypoint and an operational hub. With every added docking event and transfer, complexity increases. Spacecraft arriving from Earth must align precisely with Gateway's trajectory, matching velocity and position through calculated burns. Lander vehicles must be designed to operate in the specific orbital environment, balancing fuel allocation between descent, ascent, and rendezvous. Schedules intertwine, since delays in one vehicle's readiness can cascade into postponed missions. Consumables and spare parts must be stocked in advance, anticipating contingencies that may arise during surface campaigns. The advantage of such staging lies in modularity. Systems can be upgraded incrementally. International partners can contribute distinct components. Long-term habitation experiments can proceed independently of surface sorties. Yet modularity comes with interfaces, and interfaces require standardization, verification, and maintenance. Docking mechanisms must remain compatible across vehicles built years apart. Data protocols must align. Life support systems must integrate during crew transfers without interruption. Risk accumulates subtly across steps. A direct mission involves fewer transitions, though perhaps at the cost of flexibility. A staged mission distributes tasks among specialized vehicles, reducing demands on any single craft but multiplying the number of events that must proceed without fault. Each maneuver, each docking, each undocking represents an opportunity for anomaly, mitigated by redundancy and planning, but never entirely removed. In the silent arc of its planned orbit, the Lunar Gateway embodies an effort to create infrastructure rather than undertake isolated voyages. It reflects a shift towards sustained presence, with systems designed to support repeated missions. Yet in doing so, it layers new requirements onto an already intricate journey, weaving additional paths through space that must align with precision if explorers are to move safely between worlds. Long before hardware rises from a launch pad, another force shapes the trajectory of exploration, less visible than gravity yet equally influential. Space programs unfold within political systems that change rhythm every few years. Elections arrive, administrations transition, priorities are reevaluated. Funding allocations, though guided by long-term aspirations, are approved annually, subject to debate and revision. In this cadence, a lunar program does not exist in isolation from domestic concerns, economic pressures, or shifting geopolitical landscapes. Major exploration initiatives require commitments that extend far beyond a single term in office. Designing a new launch vehicle, developing landers, constructing habitats, and validating life support systems can span a decade or more from initial concept to operational readiness. Contracts are awarded to industries across multiple states and nations, creating networks of economic and technical interdependence. As years pass, leadership changes, and with it, emphasis may tilt toward different goals. A program conceived under one strategic vision can be reshaped or slowed under another. Budget cycles introduce their own dynamics. Agencies propose multi-year plans outlining milestones and projected costs, yet appropriations are determined through legislative processes that respond to current conditions. Economic downturns, competing national priorities, or unforeseen crises can compress available resources. When funding is reduced or delayed, schedules stretch. Testing phases may be extended, hardware production rates adjusted, workforce levels recalibrated. Even when long term support remains intact, incremental fluctuations accumulate, altering timelines in subtle ways. Large projects also demand stability in partnerships. International collaborators contribute modules, instruments, or launch services, each governed by their own political contexts and fiscal constraints. Synchronizing contributions across borders requires diplomatic continuity as well as technical alignment. A delay in one nation's budget approval can ripple through shared schedules, requiring renegotiation of launch windows and integration plans. The complexity of coordination increases with each additional stakeholder. Public perception plays a parallel role. Ambitious space endeavors capture imagination, yet sustained funding depends on broader societal endorsement. As years pass without visible milestones, enthusiasm can wane, prompting calls for reassessment. Conversely, high profile successes may invigorate support, reinforcing commitment. Communication strategies, educational outreach, and transparency become part of program management, shaping how exploration is understood beyond technical circles. Unlike the concentrated urgency of earlier eras, contemporary lunar initiatives unfold within diversified policy landscapes. Exploration competes with infrastructure, healthcare, defense, and other national investments. Decision makers must balance symbolic achievement against tangible domestic needs. The result is a pacing that reflects compromise, adaptation, and negotiation rather than singular focus. Time in spaceflight is measured not only in orbital periods, but in legislative sessions and fiscal years. Hardware awaiting integration can remain in storage as budget approvals proceed. Engineers continue refinements while awaiting authorization to proceed to the next phase. This interplay does not progress entirely, yet it modulates its tempo. A mission that might be technically feasible within a defined engineering schedule must align with political continuity to reach fruition. In this layered environment, returning to the moon becomes as much an exercise in sustained governance as in propulsion and guidance. The arc of a lunar program stretches across decades, intersecting with cycles of leadership that are comparatively brief. Maintaining momentum requires alignment between long-term vision and short-term decision-making, ensuring that exploration persists through transitions that are inherent to democratic systems. Inside a spacecraft traveling beyond Earth, gravity no longer presses steadily against the body. Muscles that once countered weight with every step now move without resistance, and bones that evolved to bear load begin to register the absence. In microgravity, the human skeleton experiences a gradual reduction in bone mineral density. Calcium, no longer required in the same structural quantities, is released into the bloodstream and eventually excreted. Over weeks and months, this shift can weaken weight-bearing bones, particularly in the hips and spine. Exercise regimens attempt to counteract the process, using resistive devices that simulate load. Yet the stimulus differs from standing and walking on a planetary surface. Muscle tissue responds similarly. Without constant gravitational demand, fibers in the legs and back diminish in mass and strength. Treadmills, secured with harnesses and advanced resistance machines, provide partial compensation, encouraging contraction against force. Crews dedicate significant portions of each day to structured workouts, maintaining cardiovascular health and mitigating atrophy. Even with such measures, measurable changes occur, requiring rehabilitation upon return to stronger gravity environments. The cardiovascular system adapts as well. Fluids shift toward the upper body in microgravity, altering facial appearance and affecting pressure regulation. The heart, freed from pumping blood against gravity, may experience changes in muscle mass and output. Upon re-entry to a gravitational field, these adaptations can result in temporary dizziness or reduced tolerance to standing. Countermeasures focus on maintaining volume and conditioning, yet the body's intrinsic responsiveness to environment ensures that change accompanies prolonged exposure. Immune function also appears to shift in space. Studies have indicated alterations in immune cell behavior and cytokine profiles during extended missions. The exact mechanisms remain under investigation, involving interactions between microgravity, radiation exposure, stress, and circadian rhythm disruption. Viral reactivation observed in some astronauts suggests that dormant pathogens can respond to the altered physiological state. Maintaining crew health therefore requires careful monitoring, vaccination protocols, and environmental control within the habitat. Psychological dimensions intertwine with physical effects. Confinement within limited volume, separation from Earth, and extended mission duration introduce stressors distinct from terrestrial experience. Communication delays and the absence of immediate rescue options amplify the sense of isolation. Structured schedules, private communication opportunities, and crew selection processes aim to support resilience. Habitability design, including lighting that simulates day-night cycles and interior layouts that provide personal space, contributes to well-being over time. Radiation exposure compounds these factors. Beyond Earth's protective magnetic field, increased background radiation can influence cellular processes, adding another variable to long-term health considerations. Shielding and mission duration limits are calculated with these risks in mind, balancing exploration goals against cumulative dose. The human body demonstrates remarkable adaptability, reshaping itself in response to altered gravity and environment. Yet, adaptation does not equate to immunity. Each system recalibrates under conditions for which evolution did not prepare it fully. Sustained presence in deep space demands ongoing study, countermeasure development, and acceptance that biological responses form part of the engineering equation. Machines may be designed to endure vacuum and temperature extremes. The body requires its own architecture of support, exercise, nutrition, and psychological care to remain robust across journeys that extend far from the familiar pull of Earth. Far from Earth, distance transforms urgency into patience. In low orbit, contingency plans often include rapid return trajectories measured in hours. Beyond that familiar envelope, geometry replaces speed. Abort windows open and close according to orbital alignment, propulsion capability, and the relative motion of two celestial bodies moving through space. A spacecraft bound for the moon cannot simply turn around at any moment and descend home. Its path is shaped by velocity and gravity, and reversing that path demands fuel, time, and precise timing. During transit, certain phases allow a free return trajectory, a carefully calculated arc that bends around the moon and guides the spacecraft back toward Earth without additional major burns. Outside that corridor, options narrow. If a propulsion system fails after a critical maneuver, the crew may face extended exposure while engineers calculate alternatives. Communication delays, though brief in human terms, complicate rapid diagnosis. Systems must therefore be designed with layered redundancy, not as luxury but as necessity. On the lunar surface, the margin for improvisation shrinks further. There is no nearby station, no quick ascent vehicle waiting beyond the horizon. A habitat must function as shelter, laboratory, and hospital combined. Power systems, thermal control loops, and life support hardware operate continuously, and any disruption can cascade through tightly coupled subsystems. A pressure leak requires immediate isolation. A power fault during the long night threatens heating systems that guard against extreme cold. Each emergency plan assumes limited personnel, constrained tools, and finite spare parts. Medical care represents another boundary. Crews train extensively in emergency response, learning procedures that on Earth would involve teams of specialists and advanced facilities. In deep space, diagnostics rely on compact imaging devices, portable ultrasound, and biochemical sensors integrated into medical kits. Surgical capability is restricted by volume, mass, and the challenges of performing procedures in reduced gravity. Evacuation to Earth may take days, even under optimal alignment. Treatment protocols must therefore prioritize stabilization and prevention, reducing the likelihood that severe conditions arise. Psychological resilience intersects with these scenarios. An anomaly in a distant environment carries weight not only in technical terms, but also in perception. Maintaining calm, structured communication, and disciplined execution becomes part of survival architecture. Crew cohesion and clear leadership mitigate the risk that stress amplifies error. Training simulations on Earth attempt to replicate isolation and uncertainty, yet real missions introduce variables impossible to duplicate fully. Surface mobility adds complexity. If a rover becomes disabled kilometers from habitat, retrieval requires coordination, power management, and suit endurance planning. Extravehicular activity itself carries inherent risk, with limited consumables and strict timelines governed by oxygen and carbon dioxide removal capacity. Every excursion is mapped against contingencies, yet unknowns remain embedded in terrain and hardware. Emergency management in deep space is therefore less about dramatic rescue and more about layered prevention, robust design, and disciplined procedure. Systems are cross-checked, components duplicated, and failure modes analyzed in exhaustive detail before launch. Even so, the environment permits little forgiveness. The absence of rapid rescue shapes mission architecture from the outset, embedding caution into propulsion budgets, habitat design, medical planning, and crew selection. In that vast separation, safety emerges not from proximity to help, but from preparation carried outward from Earth, sealed within the vessel, and sustained through vigilance across every hour of the journey. Long before any spacecraft leaves the ground, entire missions are rehearsed inside controlled rooms, where engineers attempt to compress the vastness of space into measurable conditions. Chambers are evacuated to near vacuum, thermal systems are pushed toward extreme ranges, and hardware is cycled through stresses meant to imitate launch and flight. These environments are precise, instrumented, and repeatable, yet they are still rooms on Earth, bounded by walls, cables, and gravity. Vacuum facilities can remove air, but they cannot remove scale. A chamber large enough to hold a full spacecraft is still minuscule compared to the emptiness through which that spacecraft will travel. In orbit or beyond, radiative heat exchange occurs against a backdrop of deep cold stretching infinitely outward. On Earth, even in a vacuum tank, subtle influences remain. Structural supports conduct heat. Residual molecules linger. The geometry of the test environment shapes thermal behavior in ways that differ from open space. Gravity itself introduces distortion. Components designed to operate weightlessly must often be supported during ground testing. Fluids settle differently under Earth's pull, affecting propellant management systems and life support loops. Engineers compensate with models and computational analysis, yet certain interactions only emerge when the system is freed from gravity entirely. Microgravity experiments conducted on parabolic flights or suborbital trajectories provide brief windows of insight, but sustained conditions cannot be fully replicated for long durations before launch. Software undergoes exhaustive simulation, with digital twins mirroring hardware behavior in real time. Scenarios are injected, anomalies scripted, and response trees validated. Despite this rigor, complexity resists total capture. Spacecraft are integrated assemblies of thousands of components, each with manufacturing tolerances and unique histories. When these elements interact in the dynamic environment of space, minute variances can align in unexpected ways. Vibrations from launch may loosen a connector that performed flawlessly in static tests. Thermal cycling over weeks may alter material properties beyond predicted ranges. Human systems add further uncertainty. Astronauts train in neutral buoyancy laboratories and high-fidelity mock-ups, rehearsing procedures until they become reflexive. Still, the psychological texture of actual distance, the knowledge of limited return, and the cumulative fatigue of real mission timelines introduce factors impossible to simulate fully. Team coordination evolves differently under authentic stakes. Historical missions have revealed issues that never surfaced during testing. Solar arrays have deployed more slowly than anticipated due to subtle friction in hinges. Dust has adhered in patterns not predicted by laboratory experiments. Communication systems have experienced interference unique to orbital geometry. Each anomaly becomes a lesson incorporated into subsequent designs, gradually refining understanding. Testing therefore operates as approximation rather than duplication. It narrows uncertainty, reduces risk, and builds confidence, but it does not eliminate the unknown. Engineers acknowledge this implicitly, designing spacecraft with margins and contingency procedures that assume incomplete foresight. Redundancy, fault detection, and graceful degradation become part of architecture precisely because reality extends beyond simulation. The transition from Earth-based rehearsal to flight marks a threshold where models meet environment. Data flows back, telemetry revealing how hardware truly behaves when suspended in vacuum, exposed to radiation, and cycling through day and night without atmospheric buffering. That data enriches future tests, tightening alignment between expectation and experience, yet the relationship remains iterative. Space resists perfect rehearsal, ensuring that each mission carries an element of discovery, not only about distant worlds, but about the limits of prediction itself. The architecture of Apollo carried within it an ending. Every component, from the towering launch vehicle to the fragile lander resting on powdery ground, was optimized for arrival and return, not residence. Mass budgets were calculated for days, not months. Consumables were packed with the understanding that they would be used quickly. Then the crew would depart. The lunar surface was a destination to touch, study briefly, and leave behind. Mission timelines reflected this intention. Surface stays lasted hours at first, then a handful of days as confidence grew. Experiments were deployed, samples collected, photographs taken. The emphasis rested on demonstration and proof, on showing that navigation, landing, extravehicular activity, and ascent could all be executed successfully. Infrastructure was minimal because permanence was never the mandate. There were no plans for power grids stretching across regolith, no buried habitats shielding occupants from radiation, no supply chains extending year after year. Political context shaped that brevity. Apollo emerged from a race, and races conclude when the finish line is crossed. Once the objective of landing humans on the moon and returning them safely was achieved, the strategic urgency that had fueled extraordinary investment began to diminish. Subsequent missions expanded scientific return, traveling farther with rovers and carrying more instruments, yet the fundamental design remained transient. Each landing site became a quiet monument the moment ascent engines ignited. Long-term habitation presents a different class of challenge. Sustained presence requires redundancy in every life support system, robust shielding against radiation and micrometeorites, reliable energy production through long lunar nights, and logistical frameworks for resupply or local resource utilization. Apollo hardware was not constructed with these requirements in mind. The lunar module ascent stage, delicate and lightweight, was engineered to lift two astronauts from the surface into orbit once. It was not intended to cycle repeatedly between surface and orbit, nor to support extended habitation. Even the spacesuits, remarkable for their era, were tailored for limited excursions. They endured abrasive dust and temperature extremes for short durations. Extended deployment would have demanded different materials, maintenance procedures, and storage systems. The command and service module orbiting above provided life support and propulsion for the journey home, yet it too was built for a singular voyage. Financial trajectories reinforced this structure. As funding levels declined after the early triumphs, ambitions narrowed accordingly. Proposals for lunar bases circulated within planning documents, envisioning modular habitats and nuclear power units. None progressed to realization. Public attention shifted, and national priorities evolved. The moon remained where it had always been, but the program designed to reach it concluded with the tools it had built. Thus, Apollo did not stay, because staying was never encoded into its blueprint. It was an expeditionary effort, comparable to a voyage across an ocean undertaken to prove that the crossing was possible. The ships returned home. No harbor was constructed at the far shore. What remained were instruments left in silence, reflective panels still returning laser pulses, and footprints undisturbed in vacuum. The absence of permanence was not failure but design choice, aligned with objectives defined at the program's inception. In that design lay both its brilliance and its limitation, a reminder that visiting and inhabiting are distinct endeavors, requiring distinct commitments. There is a quiet distinction between stepping onto a landscape and choosing to remain within it. A visit is measured in hours or days, framed by departure already scheduled. Living extends beyond the horizon of return, reshaping priorities from immediate survival to continuity. On the moon, that difference unfolds in layers of engineering, logistics, and human adaptation. A short mission can rely on concentrated reserves. Oxygen, water, food, and power are calculated precisely for a defined span, with margins carefully bounded. Equipment may tolerate gradual wear because it need only function briefly. A lander can be optimized for minimal mass, accepting fragility in exchange for efficiency. The crew's objective centers on exploration, sampling, deployment of instruments, and safe ascent. Time is precious but limited, and the architecture reflects that brevity. Months alter every assumption. Consumables become cycles rather than stockpiles. Oxygen must be generated or recycled continuously. Water systems must reclaim moisture from air and waste streams with high efficiency. Food storage expands or shifts toward partial local production. Power generation must persist through long lunar nights, requiring energy storage solutions far beyond what a short stay demands. Reliability transforms from desirable to essential, as systems must endure thermal cycling, abrasive dust, and radiation without immediate replacement. Shelter during a visit can be compact and temporary, a pressurized volume designed for rest between excursions. A habitat for living demands layered protection and psychological consideration. Radiation shielding may incorporate regolith piled above structural modules. Interior spaces must support work, exercise, privacy, and communal interaction. Lighting systems simulate circadian rhythms to anchor human biology in an environment without natural atmospheric cues. Maintenance becomes routine rather than contingency, with spare parts cataloged and tools organized for repeated use. Exploration emphasizes mobility and discovery. Infrastructure emphasizes stability and growth. Establishing landing pads to reduce dust plumes, constructing berms for protection, deploying communication relays, and assembling modular expansions all shift focus from singular achievement to cumulative presence. Robotic precursors may prepare terrain, level surfaces, and pre-position supplies before crews arrive. The moon transitions from destination to workplace. Risk profiles diverge as well. A brief mission accepts concentrated exposure, relying on swift return to mitigate long-term effects. Extended habitation accumulates radiation dose, mechanical fatigue, and psychological strain over time. Countermeasures must scale accordingly, integrating shielding strategies, medical monitoring, and social structures that support well-being across seasons rather than days. Economics intertwine with these technical realities. Visiting can be funded as a discrete project with defined milestones. Living implies sustained investment, supply chains, and policy continuity across years. It requires coordination between launch providers, habitat designers, energy specialists, and life support engineers in a steady cadence rather than a singular surge. The physical surface remains unchanged, silent, and airless. What changes is intent. To visit is to leave footprints and depart. To live is to lay foundations and return repeatedly. The tools, systems, and commitments differ not only in scale, but in philosophy. One approach proves capability, the other builds permanence. Between those paths lies the transformation from expedition to settlement, a shift that extends far beyond propulsion and landing, reaching into every subsystem that sustains human presence beyond Earth. Beyond the familiar arc toward the moon, another destination reshapes the entire architecture of planning. Mars lies far more distant, months away, along trajectories that stretch through interplanetary space. Yet its environment introduces conditions absent on the airless lunar surface. The contrast alters propulsion budgets, habitat design, entry strategies, and even the philosophy of exploration. The journey itself extends across half a year or more, depending on alignment. Crews must inhabit their spacecraft for durations far exceeding a lunar transit, carrying life support systems capable of sustained autonomy. Radiation exposure accumulates over longer intervals, and communication delays expand from seconds to many minutes. Real-time guidance from Earth becomes impractical, requiring greater onboard decision-making and resilient operational protocols. Distance deepens isolation, and mission architecture must anticipate that assistance remains far beyond immediate reach. Upon arrival, however, Mars offers a thin atmosphere, Though tenuous compared to Earth's, it provides aerodynamic drag during entry. Spacecraft can exploit that drag to shed velocity, combining heat shields, parachutes, and retropropulsion in layered descent sequences. The Moon permits none of this. Every meter of deceleration there demands rocket thrust. On Mars, the atmosphere becomes both ally and hazard, generating intense heating while enabling controlled braking. Engineering solutions diverge accordingly, with aeroshell design and supersonic parachute deployment central to Martian missions. Gravity also differs. Mars exerts roughly 38% of Earth's gravity, substantially more than the Moon's 1/6. That increased pull influences human physiology, potentially mitigating some aspects of bone and muscle loss compared to prolonged microgravity or lunar conditions. Surface operations would feel more natural, though still lighter than Earth. Structural loads on habitats, mobility systems, and launch vehicles departing Mars must account for this intermediate gravity, shaping mass distribution and propulsion requirements. Resource strategies shift as well. The Martian atmosphere contains carbon dioxide, opening pathways for in situ resource utilization. Chemical processes, such as the Sabatier reaction, can convert carbon dioxide and hydrogen into methane and water, enabling local production of propellant for return journeys. Water ice detected beneath the surface offers potential for life support and fuel generation. On the Moon, oxygen can be extracted from regolith minerals, yet the absence of a substantial atmosphere narrows options. Mars therefore presents a broader palette of materials, though extracting and processing them demands energy and infrastructure. The concept of the Moon as a stepping stone emerges from these contrasts. Proximity allows iterative testing of habitats, power systems, and surface operations under reduced gravity without the extended transit times of a Martian expedition. Communication remains nearly instantaneous, and abort trajectories are measured in days rather than months. Lessons learned in dust mitigation, radiation shielding, and life support reliability can be refined closer to Earth before committing to the longer voyage. Mars planning thus unfolds as a synthesis of greater distance and richer environmental complexity. Entry, descent, and landing leverage atmospheric physics absent elsewhere. Surface habitation considers both gravity and resource availability in ways unique to that planet. The Moon serves as rehearsal space, not because it replicates Mars exactly, but because it allows gradual expansion of capability beyond Earth's orbit. Between these worlds lies a continuum of challenges, each informing the next, shaping exploration not as repetition, but as progression outward through differing conditions and opportunities. Across the decades since the last ascent engine flared above the lunar horizon, the surface has remained as it was, silent and unaltered. Craters cast the same sharp shadows. Regolith lies undisturbed where no wheel has passed, and the vacuum holds its steady absence of sound. The Moon has not grown more distant, nor has its gravity deepened. The equations that govern transfer orbits and descent profiles remain intact. What has shifted is the context from which we approach it. Risk is weighed differently now. Earlier eras accepted uncertainties that would be reconsidered under contemporary standards. Losses that once were framed within geopolitical urgency would today reverberate across a global audience in real time. Engineering culture reflects that change. Layers of review, verification, and redundancy accumulate around every subsystem. Designs evolve through extended testing cycles, simulations, and independent assessments. Caution becomes embedded not from fear, but from accumulated experience and expanded accountability. Budgets trace similar transformations. Large scale programs now unfold within financial landscapes that distribute resources across numerous priorities. Sustained funding requires consensus that extends beyond a single administration or moment of competition. Projects must justify long timelines and incremental milestones, balancing ambition with fiscal constraint. This environment encourages phased development, partnerships with private industry, and international collaboration, each adding coordination, complexity, alongside shared capability. Public scrutiny has intensified as well. Information travels instantly, and every delay or anomaly is examined broadly. Transparency strengthens trust, yet it also magnifies setbacks. Agencies respond by documenting processes meticulously and communicating cautiously, aware that perception shapes support. The collective memory of past triumphs can compress the challenges that preceded them, making renewed efforts appear slower by comparison. Engineering itself has grown more conservative in critical domains. Safety factors are recalculated with expanded datasets. Human rating requirements demand comprehensive fault tolerance. Autonomous systems must prove reliability across extended durations before crewed application. The aim is not spectacle, but sustainability, constructing architectures that can endure repeated missions rather than singular demonstration. None of these changes alter the environment awaiting beyond Earth. Space remains hostile to unprotected biology and fragile machinery. Radiation streams through vacuum without obstruction. Temperature extremes swing without atmospheric moderation. Micrometeorites continue their quiet impacts. The moon offers no shelter by default, no breathable air, no forgiving margin for error. It is as indifferent now as it was when the first boot compressed its surface. Returning, therefore, is not barred by impossibility. The propulsion principles are understood, materials are stronger, computing power vastly greater. Yet the challenge unfolds within a different framework of expectation and responsibility. Building systems that satisfy modern safety standards, operate within constrained budgets, and aim toward sustained presence rather than brief visitation requires broader coordination and deeper resilience. Memory can compress complexity into a single image of triumph. With distance, the intricate scaffolding of effort recedes, leaving only the moment of arrival. When examined closely, that earlier achievement reveals extraordinary concentration of resources, risk acceptance, and focused intent. To repeat the act under present conditions demands adaptation rather than nostalgia. The moon has not changed, but we have matured in how we measure risk, allocate resources, and define success. The path back threads through this evolved landscape, shaped by caution and continuity. In that recognition, the mystery settles into clarity. There is no failure in the delay, no betrayal of past accomplishment, only the steady reality that physics and survival impose their terms without haste.